Alright guys, just before the holidays I'm going to leave you with the hyperbola. I'll see how I go in explaining this one, and then I might just leave you with the parametric equations without a proof. I might just give those to you. They aren't a huge part of our internal anyway. So you guys would have seen a hyperbola before, but not really like this. What you would have seen actually is something more like you would have had a Cartesian plane or an XY axis, and your hyperbolas would have done something like this. And if you did year 11 graphing, you would have just moved that around. So you may have had something like this, but they're always perpendicular. So now what we have now is non-perpendicular asymptotes and things like that are going to get quite interesting. So let's define a hyperbola. Like all our conic sections, they have focus points. So F2 and F1 focal points. So the definition is, and it's again the locus, the locus of a point that moves, so it's the difference of the distances from each point to a fixed point is constant. So I'll write that down. So the locus or locus, I'm not actually sure I've only ever read it, the locus or locus of a point that moves so that I'll write this in a different color, so that the difference of the distances to the point from each focus is constant. So the locus of a point that moves, so its difference of distances to the point from each focus is constant. So what does that mean? It means that if I was here and I took that distance and that distance, I took the difference between them, it would be some constant. So if I called that P, then P F2 minus P F1, so P F2 being that line, take away P F1 being that line, is equal to some constant. And so if I was over here and I took that distance and this distance, then P, and that was P, then P F1 minus P F2 would be equal to that same constant. Now remember that the ellipse was the sum of those distances was constant, right? Remember the sum of those two distances was constant, and then it gave us an ellipse. Well, the hyperbola is like the inverse of that, and I like to think about it as the ellipse that's being turned inside out, and is now everything shooting off that way. So the equation, the Cartesian equation, is x squared over a squared still. Y squared over b squared is equal to 1. And the only difference between this and the ellipse is it is now a subtraction. It's the difference between those two distances. Okay, so what we're going to do now is I'm just going to define a few things. So we still call these the vertices. Those are the vertices, but this here is the center. So halfway between the vertices is the center. The two foci are at C0, negative C0. So C0, negative C0. And there's a ABC relationship again, and that is b squared is equal to c squared minus a squared. And I'm going to give you the relationship of a and b in a second. So that's the center, and the line segment joining the two vertices is called the transverse axes. So from here to here, this here, that is called the transverse axes or axis. All right, and its length is 2a. So the transverse axis is 2a. Okay, so a is the distance from the center to a vertex, just like when the ellipse went around. Okay, it was from the center. It was like your major axes or minor axes. So transverse axis is 2a. And what a hyperbola also has, it's getting a wee bit messy now, but it has what we call asymptotes. So you would have one asymptote going through there, and you might have another asymptote going through, and these should go through the origin, but I haven't drawn it particularly well, and another asymptote going through there. Okay, so here is your C value. Okay, so C is from your center to the focus, A is from the center to the vertex, and so you can see how you would get B. Okay, it's a little different to the ellipse, right? And you have asymptotes, and so the gradient, the equation of these asymptotes, actually, the equation is that would be b over a x, and this one is simply just negative b over a x. And obviously there'll be some movement once we start to move this ellipse around. These lines are also going to have movement. So that is pretty much everything you need to know about the hyperbola. So let's go ahead and look at an example. So let's say we're looking at x squared over 9 minus y squared over 4, and now that equals 1. So if we were wanting to draw this, well, it's centered at the origin. There's no movement, there's no changing, there's no constants being added to the x or y in this equation. So it's just going to look like this, and arrows because it goes on forever. Okay, now a we know is 3 because that was a squared, so a is 3. So that length there is 3, and that length there is 3. So the vertex is at 3, 0, and negative 3, 0. And what else? We know that the asymptote line, so the line's going through there, we know that that's y is b over ax because it's going through the origin, so no y-intercept for our great slope-intercept equation. So b is 2, and that's 3 over x, and this one that's coming down through here, that is y equals negative 2 over 3x. Now the only other thing we want is our focal points, and so we know that b squared is c squared minus a squared, so that's going to be 4 is equal to c squared minus 9. So we'll add the 9, 13 is c squared, and so c is square root of 13, 3.606 is c. Makes sense to be a wee bit more than 9 and a bit less than 4. So c is 3.60, and so our focus is at 3.6060, and our other focus is at negative 3.606. So what you notice about this, what makes this year 13 internal so easy, is that we get equations and all we have to do is compare with the equation. So we're just comparing with, all you have to do is compare with its general formula. We're just reading off the A, reading off the B, using that in a relationship to find C, and then you're plugging in all the information that you might need. I think that's all for the hyperbola. We do have parametric equations of the hyperbola as well, and I'm not going to go ahead and prove any of those, but I will just give you those now. You won't really be asked for the parametric equation of a hyperbola. I don't think ever actually in this internal. The hyperbola though, parametric equation, so I might just add this to this sheet here. So parametric, we have x equals a sec theta, y is equal to b tan theta. The proof of that is a little bit outside the realms of our internal, but if you were just comparing with the Cartesian equation, you just put a in, b in, and you're pretty much done. If there was some movement, so some x1, you just add that x1 or add that y1 to it, because that's just some constant shift. Hopefully it helps. I'll be assigning a few questions on that hyperbola. Awesome.